So we've reached what is really the most important of all the derivative formulas. Um, I mean, all the derivative formulas are important, but some of them are more obvious than others. You know, the fact that the derivative of a sum is the sum of the derivatives, the derivative of a constant multiple is a constant multiple of the derivative. Even the product and quotient rules, they're not what you expect, but they're not especially deep in the sense that once you kind of get them, you apply the formula. But the chain rule is something else. The chain rule is really expressing something fundamental about the nature of the composition of functions as far as rates of change are concerned. So I think it's worth taking the time to think about what it's really saying at an intuitive level. I think there's a lot of students when they're taking calculus the first time, they approach something like the chain rule from a very symbolic, procedural point of view, which is fine because you definitely need to know how to use it. You need to be able to calculate derivatives. But I think you should go beyond just trying to use it. You should really try and understand what the idea behind it is. Because that idea, if you go on in math, especially in other calculus classes, like in multivariable calculus and differential equations, you're going to run across the idea of the chain rule in more than one situation. So here's one way of thinking about the chain rule. Here's an analogy that I use. The chain rule does tell us how to differentiate a composition of functions. Remember, that means one function followed by another. So for instance, all these functions here, cube root of 5x plus 1, sine of 3t minus 2, e to the minus x squared. We have no way of differentiating these yet. We can differentiate a cube root. We can differentiate a polynomial. We can differentiate the sine function, the exponential function. But these functions are combinations of those functions put together in a special way, of one followed by another. And there's no rule that we have so far to be able to find the derivative. So how are we going to get a hold on this? I mean, as I say here, we could apply to the limit definition, but that seems like, one, it's not going to be very successful, and two, why do we want to beat ourselves up like that? So the chain rule does provide us with a way to do that. So here's an example that I've often gone through to explain what the chain rule says, and it has to do with, it's going to sound a little contrived at first, but if you understand what this is saying in this more straightforward situation, it's really all that the chain rule says in terms of calculus situation. So here's the idea. So we have three people are picking apples from a tree. So there's Fernando, Uma, and Xavier. And yes, I didn't just pick those names arbitrarily. I picked them because the first letters of the name, you'll see as we go on. So suppose that Fernando picks apples 3 times as fast as Uma. Uma picks apples twice as fast as Xavier. Okay, so got that in your mind. The question then is, how much faster does Fernando pick apples compared to Xavier? And let's just assume, for the sake of simplicity now, that they're all picking these apples at a constant rate. In other words, it's not like one person is picking apples up really fast and then slowing down and taking a lunch break and so on. They're just very methodically, constantly, continuously picking apples at a constant rate. So intuitively, I think even if you ask most people who are not in a calculus class or, not even really thinking too deeply about the problem, they would say, well, let's see, if one guy is going 3 times as fast as somebody else, and then they're going twice as fast, seems like overall the fastest person would be going 6 times as fast. 3 times 2 is 6. So for instance, if in the time that it takes Xavier to pick 10 apples, Uma's picked twice as many, 20, and then Fernando's picked 3 times as many as that, which is 60. So the overall ratio is 60 to 10, or 6. So let's see if we can make this a little bit more precise. And this was what's going to allow us to get at what the chain rule is saying in general. So if we let F be the number of apples in Fernando's basket, okay, so I'm not even saying like this is a function of time. I'm just saying, just let F be however many apples are in his basket. U is the number of apples in Uma's basket, and x is the number of apples in Xavier's basket. Then we have this expression here. Now, I'm using Leibniz notation, like for derivative, but don't think of it necessarily as a derivative here. Just look at it as just expressing something about the constant rates of change. So I'm going to say df by du is 3. That's simply going to express the fact that Fernando picks apples 3 times as fast as Uma. So it's saying that the change in the apples in Fernando's basket is 3 times whatever the change in the apples in Uma's basket. While du by dx is 2, that expresses the fact that Uma's picking up the apples twice as fast as Xavier. Now, when we ask how much faster Fernando picks apples compared to Xavier, we're really asking for df by dx, okay? We're asking what's the comparison of the change of Fernando's apples to the change of Xavier's apples. Now, if you just formally play around with the Leibniz notation, here's what you get. So we get this df by dx is df by du times du by dx. Now, we know this is 3 times 2 equals 6, but the manipulations here, with the Leibniz notation, this is not quite the same as algebraic manipulations with real numbers. So it's not like the du is a number that we're canceling, but it's very suggestive, isn't it? Right? It looks like as if these were real quantities, it's almost as if I were taking, one number divided by another, and then that number showed up in the numerator, and then I was kind of canceling them. So that's not exactly what's going on here. Nevertheless, by canceling du as if it represented a real number, it seems very intuitive. It seems to express the fact that the overall rate of change is the product of the two individual rates of change, which is 3 times 2, which is 6. And it does seem to reveal a deeper truth. Okay, so here's the punchline, what the chain rule says. If you understand exactly what we went through with the constant rates of change about how fast they're picking up apples, here's what the chain rule says. So all that the chain rule says is that the above analysis that we just did concerning constant rates of change is also true for instantaneous rates of change. So the analysis we did for constant rates of change over actual periods of time, like from 12 o'clock to 1 o'clock p.m., the chain rule says that same kind of thinking that you just went through is also true for instantaneous rates of change at a single instantaneous moment in time. Pause the video, rewind, and watch it, read through that again. Read through it 2 or 3 times until you start to get at what it's saying, because this is really fundamental. This is really revealing something that if you understand this, you'll really understand what the chain rule is saying. It's saying if you have the composition of functions, we can find the overall instantaneous rate of change by multiplying the instantaneous rates of change of the functions that make up the composition, just like we do for constant rates of change. So let's look at one more example. And on this one, I'm going to ask you to pause the video and try and work out what everything means here. We're not doing a calculation. It's just an explanation. It's just trying to apply what we went through before and apply it to a new situation. So suppose we're climbing up a mountain. Well, as you climb up a mountain, your altitude, which is the elevation, we'll call that A. That could be a function of time, because you're going up the mountain. At the same time, as you know, as you go up a mountain, the atmospheric pressure is going to change as well. Okay. So the pressure, you could say, is a function of altitude. So we have A as a function of T, P is a function of A. Overall, that means that P is a function of T. It's a composition. The pressure depends on the altitude, which itself depends on the time. So if you give me a time, I can find the altitude, and from the altitude, I could find the pressure. So there's a function P of T. So explain what this equation means. dP dt equals dP dA times dA dt. express what this means in terms of composition of functions and the chain rule. So go ahead and pause the video, just write out in words what this is saying, and we'll come back in a sec and talk about it. All right, so let's go over what each of these is saying. So let's start with the right-hand side, dpdA. So this is the instantaneous rate of change of pressure with respect to altitude. Okay, so this is saying as I go up, as I go up the mountain, the pressure is changing with respect to my altitude. So it doesn't have to do necessarily with how fast I'm going up the mountain. It's saying like for every meter that I go up the mountain, the pressure changes by this much. Okay. And it's an instantaneous rate of change. So what is dA dt saying then? Well, dA dt, that's saying how fast am I going up the mountain? So how many meters per minute or so. So it's the instantaneous rate of change of the altitude with respect to time. So it's saying how fast something is happening. How fast am I going up the hill as far as elevation? So what this equation is saying is if I multiply those two together, if I say this is how fast I'm going up the mountain, times this is how fast the pressure is changing with respect to my altitude or elevation, if I multiply those two together, I'll get the instantaneous rate of change of how fast the pressure itself is changing with respect to time. That's what dp dt is. This is the instantaneous rate of change of pressure with respect to time. And just to get a sense of how you would use this so what you would think that this would mean in practice, just think about changing some things. So what this is saying is that there's two ways that I could increase the pressure, could increase faster. How can the pressure change faster? Well, it means I could either go up the mountain faster, or maybe I'm at a point of elevation or altitude where the pressure is changing really fast at that altitude. Those are two ways that the overall pressure could change very quickly. So it's saying that dp dt, this rate of change, is equal to the product of dp dA and dA dt. Just like getting apples 3 times as fast multiplied by getting apples twice as fast overall meant you're getting them 6 times as fast. The main difference here is, when you're doing comparing apples, how fast they're getting apples, they're kind of the same units of things, whereas here there's really 3 different units going around, right? There's the units of pressure, whatever that is. There's the units of altitude, however you choose to measure that, and then the units of time. But it's the same basic idea. If you notice, whatever those units are, you can do a little unit analysis here, right? Notice if I do a dimensional analysis, the units have to cancel as well. So remember, the instantaneous rate of change with the derivative is always the units of the dependent variable divided by the units of the independent variable. So whatever the units are on the bottom there, they're going to cancel with the units on top of the dA dt, and overall you're just left with the units of p divided by the units of t, which is as it should be because that's exactly the units that you get on the left-hand side. So the units also agree. So, I hope this makes sense. Like I said, you don't have to understand it at a deep level, like in the core of your being, to be able to do the homework problems. In fact, it's probably possible to really understand what this is saying and be really bad at using the chain rule symbolically, because that takes practice, and if you haven't practiced it, it doesn't matter, how much of a theoretical understanding you have of it, you're not going to be able to do the problems. But I think it's important to do this because calculus is about ideas. It's contrary to popular opinion. It's not really about memorizing a bunch of formulas. There's a handful of key ideas and, big ideas going on that if you get those, you're going to be able to orient yourself to everything that's going on in the class. So in the next section, we'll go on and we'll look more at the chain rule in practice. So we'll write down what the chain rule is, and we'll do a whole bunch of derivatives using the chain rule, and those will be more like homework problems, but I wanted to go through this before we actually did that. Okay, so I'll see you then.